Hello everyone. In this video lecture we're going to be going over solids and abacus. So this is the example that we did in class already. Just one thing that I wanted to mention again, one of the things that we take advantage of when we do these simulations is symmetry. So in this part we have symmetry in both the x and the y direction. So we don't actually have to do a simulation on the entire part. We can cut it into a quarter and then just set boundary conditions in both the x and the y direction in order to run the simulation. And the advantage of this is we don't have to use as many elements, which is especially useful in our class because we have a student edition of abacus and we're only going to do 1,000 nodes. Also, one thing to note about this image, we don't have any fillets on the inside squares. And as we discussed in class already, if we were to run the simulation, we would never get the stress to converge, as in if we increase the mesh size, the stress concentration is just going to keep increasing and we're never going to get a constant stress, and we're just going to keep increasing the stress value. So we're going to go ahead and go into abacus and draw the part. So this is much the same we've done before, so go ahead and click part. We're going to be doing 2D planar and we're doing a deformable shell. And approximate size 10 is fine, which is the size of the part that we're making. So we're just going to create a full square and dimension the part accordingly. Now, as I said before already, we're only be doing the top left part section of the piece. So we're just going to be looking at only one window, essentially. So we're just defining the coordinates. Each of the middle edges is just 1 unit away from the outer edge. Cool. So we've now created our initial part. But as I said earlier, if we were to just run the simulation using this, and you can try it yourself, we would never get the stress to converge. So we want to add fillets to the inside pieces, which is where we're going to have our max stress concentration. So there's a fillet button on the left here, and it'll ask you fillet radius. And we're just going to create a radius of 1 on the part at each corner. And then we click enter, and then it says select the entities to fillet. So we select the first edge that we want to be filleted, the second edge, and it'll create a fill between those 2 edges. So we're just going to click on each edge to create all the fillets. So the reason why we're not going to fillet the top left edge is because that's not where the max stress concentration occurs. So it's really not a factor in this simulation, and it also would affect the loading condition as well, because the top surface geometry would be changed slightly. So it's just more convenient to keep that edge not filleted. So just click escape and done, and we've created our part. So now, as before, we have to define the material and mechanical elasticity. We have a Young's modulus of 200 gigapascals and a Poisson's ratio of 0.3. Okay, and now we want to create each section on the part. Now, for this, we're doing solids. We're no longer working with beams or trusses. So for the category, select solid, and we're just doing a homogeneous type. And the plane strain's thickness should be specified and is of 1. Type in 1, okay. Cool. So now we want to assign our section to the part. So click assign, section, select the part, and done. So we have now assigned our section to the part. So now we're going to go into our assembly and create our instance. So open up assembly, open up the tree, instance. And we're just going to do a dependent instance, which means that we're going to be meshing on the part instead of on the instance, and you'll see how that changes later. So go ahead and click OK, and we'll see our instance has been created. So now we need to go ahead and create our loading and boundary conditions. So we need to go to steps and right click and create a step. Create. And this is the same thing we've been doing earlier. Static general, linear perturbation. Nope, linear procedure type, linear perturbation. And click continue. Okay. So now we're going to open up the initial tree to make our boundary conditions. So as I said earlier, we can take advantage of symmetry of this part. So we're going to do a symmetry or anti-symmetry and concentrate. Continue. So for the bottom face, this is going to be fixed in the Y direction. So we click this place, click done, and we're going to fix it in the Y direction with symmetry. Okay, and now for the right face, it's fixed in the X direction. So go ahead and create another boundary condition, and we'll fix it in the X direction with X symmetry in all directions. Cool. And now we can see that this is just the top left of the part. So if we were doing the top right, we would do the loading conditions on the left and the bottom face. Now you're going to see the same stresses just in different places. So now we need to create our loading condition. So loads, mechanical, we just have a uniform pressure force on the top face. So click pressure to make that distributed load. Click the top face, done. And the magnitude, I believe if we go back to the other part, to our thing, it's 100 newtons per meter. So pressure force is always going inward on the part, so we need to make it negative so that it pulls outward. And click OK, and we'll see our load on the top. So this is our boundary and loading conditions, as you can see here, and everything looks correct. So now we're going to go ahead and go to the meshes, which is the main difference for solids. So go ahead and click mesh, and we're going to click on the part. So on the top there it says object assembly. So before we did an independent instance, which means we're meshing on the assembly, but since we're doing dependent, we're meshing on the part. So go ahead and click the part. So we're good now. So go up to the mesh bar at the top, and now we're going to click on mesh controls. So here you can see there's three options: quad, quad dominated, or tri. So we discussed this in class already. What we're going to be using is a Q4 element type, and the reason why we're doing that is because it has the most accurate results, but we're only going to be doing 4 nodes because of the limitations that we have, and it also makes your runtime quicker, especially if you're doing large simulations. So if we wanted to do a CST, we would click try, and that would be a 3-sided element. But we're doing quad, so okay. So now we've defined our mesh control. We need to go ahead and define our element type. So we already established our shape, and now we need to establish what we want to do with that shape. So select the whole region, and we're going to be doing standard, linear. If we wanted to do a Q8, we'd be doing a quadratic, but since we're doing Q4, we're doing linear. Unchecked, reduced integration, and on the bottom, you'll see it says a 4-node bilinear plane stress quadrilateral, which is what we want. So click OK, and click done. So now we want to seed our part. So go ahead and click seed, part. Now I'll show you the issue that occurs when we just do a seed on the global scale for this part. So we can just do an approximate size of 0.5, that'll work. Click apply, and click OK, and let's do mesh part. So as you can see, we kind of have a somewhat of a messed up mesh. There's nothing really particularly wrong about it, but it's not symmetrical, and we want to make it look nicer. So we did this in class as well, and we're going to add a partition in order to direct our mesh. So essentially we're going to create a sketch on the part that defines where we want the mesh to go. And the regions that we really are worried about is the fillets, so we're going to define how the mesh leaves from the fillets. So let's just go ahead and delete this mesh first, because we're not going to be doing this type of mesh. So delete part native mesh, yes. And now we're going to go ahead and create our partition. So go ahead and open up parts. So if we go to tools, go ahead and exit out of this. We don't want to do this. Go ahead and go to tools. Customize. Actually, X out of this. X out of this. Cool. So if we go to tools, cancel. You'll see here there's partition, and this will allow us to create a partition on our part. So go ahead, and we want to do a face partition, and we're going to create a sketch. So now that we're just going to draw the mesh in the way that we want to. Now, if you went to class, you'll know that we're worried about the fillet regions. So go ahead and click Create Lines, and we're going to draw a line from the outer edge to the inner, to the center of the fillet. And this is going to break up our fillet into 2 separate sections. Go ahead and do that for that one. And we'll do it for each section. And this is so we have 2 defined regions for elements. Cool. And now to make it better as well, we're going to draw line segments from the outer edge of the fillets to the edge of the part. Go ahead and click Escape. So for one of the examples or for one of the problems that you have on your homework, you have a rectangular piece with a circle in the middle. Now, she already drew the dotted lines across the part, but you have X and Y symmetry of the part, so you can essentially split it up so that you're only doing the top right quarter of the part and you're only doing a quarter of the circle as well. So it would basically be like having one fillet. And now we can trim the part. We don't want to click the eraser, that'll erase the whole thing. So if we go to the left, there's a trim tool. Go up a few more. Up one more, down one. There. So now we can auto trim the part. And we'll just select the edges that want to be trimmed. So done. So we've now created our partition that we're going to be going by. And as you can see, this is just going to direct the mesh, and we can seed the mesh accordingly. So we can seed each edge of this partition. So if we go back to mesh, so click done. Go back to mesh. So now we already have our mesh control and element type defined. We just want to do the seeding. Click seed. Edges. So we're going to seed by the edge. Now, let's go ahead and start by doing the inner radius of the fillets. So one thing you could do is do a single bias picking if you go to the bottom. And if you check this box, what it's going to do is it's going to make a finer mesh towards the side of the edge that you picked. So let's say we picked towards this edge here. Our mesh is going to get finer towards the outer edge of the radius. Now you can also do that for the segments extending to the end of the part if you want to make a finer mesh going towards the center of the fillet as well. But let's go ahead and uncheck that just to make a neater mesh. Let's go ahead and seed, edges, and uncheck single bias picking. And we'll select all the fillets here. So select this fillet and go ahead and select them all. Excuse me. And now these edges are connected to the outer edges of each segment. So we're going to also select the outer edges as well. So we're basically telling it we're going to be wanting a certain number of elements going from this edge to this edge. And I'll show you that soon. So now if we click done, it's going to ask us how do we want to seed the part. And we don't want to seed it by size, we want to seed it by number of elements. And we're not going to do a bias for this one, so we're going to click no bias. But let's say we want to do 4 elements along the edges. So we'll type in 4. So it's going to create 4 elements across each surface that we picked. And the reason why we also picked the outside surface is so that we have the same number of elements on the inside and the outside. And this is going to help create a uniform mesh. So now that we've selected those inner and outside ones, we want to select the number of elements going outward. So we're going to go seed edges, and now we're going to select the middle section of each part. And let's do a single bias picking because we know the maximum stress is going to be towards the fillets, so we don't really care as much about the stress on the outside of the part. So we click single bias picking, and we'll select closer to the fillet. That way that the mesh is biased towards the fillet. So we'll select towards the inside edge here. Select the inside edge there. And we can do it on every vertical and horizontal piece. So just select all the rest of the edges. Mm. So done. So now we have a certain number of elements going towards the center. Now you'll see your arrows are pointing towards the center, and that's because we clicked towards the center of the part, which means that the mesh is going to get more fine towards the center of the circle. So now there's two things that we can click. We're going to have a bias, so we do the method by number, bias a single bias, and there's a bias ratio and a number of elements. So the bias ratio is just how much you want it to be concentrated. We can do a bias ratio of 3 for this one, so it's not too heavy of a concentration, and we'll do the same number of elements as of 4. Go ahead and click apply. Now, we've left the middle square regions of each part blank right now. So the benefit of partitioning your sketch is you can create a different number of elements in each region. So in the other regions, we created 4 elements across each edge. But let's say we only want to have 2 in this region, because we know this is where the stress concentration most likely won't occur. So this is not where our max stress would be either. So we can go ahead and seed these edges. Go ahead and click seed. And now select each edge. And we're not going to do a bias either, because we don't expect the max concentration to be here. So done. And we don't want to bias, so click none. And let's say we want 2 elements, because we don't want to have as much as the other sections. Okay? And the benefit of that is we save the number of nodes we have. So in this example, it's not really saving us much, but if we're doing a bigger part, it could save us a lot. So go ahead and click done. Now go ahead and click mesh part. So as you can see here, we have a pretty nice looking mesh, and we have those 2 bigger rows of elements where we made the larger mesh size. Okay, so now that we've made our mesh, we can go ahead and submit our job. So this is nothing new. Just okay, right click submit. And okay. And it tells us we've created 160 elements. Now go ahead and review the results. So on your homework, it should be asking you, what is the von Mises stress? So the von Mises stress is used for your failure criterion, which is why we choose this. So if we're trying to see when the stress is going to fail, we'll click on von Mises stress and see if it reaches our yielding point of the material. Okay, so as we can see here, as expected, our max stress occurs on the edge of one of the fillets over here. And this is towards the left side of the part. Now, you may be asked, does this stress converge? And in order to see if the stress converges, we'll need to increase the number of elements in that region. So right now, we just have a stress, but what does that stress actually mean? Is that the actual stress in the part, or is that just a stress in the simulation? And it's just a stress in the simulation based on the number of elements we chose. So in order to be confident that that's the actual stress seen in the part, we need to increase the number of elements in that region, which is the same thing as in making a finer mesh in the part. So if we go back to mesh, we can now click seed. We're going to be using the same element type, but now we want to change the number of elements along our edges. So we knew this region here is about where our max stress concentration occurred. So we can click this edge here and this edge here, and we'll increase the number of elements in that region. So instead of doing 4, let's do 8. We also, and we're gonna have to delete the meshes in that region, okay? And we also noticed that the stress was kind of along that whole edge, so let's go ahead and increase the number of elements in that region below there as well. So yeah, in this region here, let's go ahead and increase the number of elements there. Done. And let's go ahead and put 8 elements there as well. Apply. So now let's go ahead and mesh the part again. Click done and mesh part. It's kind of a janky mesh, and the reason is because we don't have the same number of elements leaving the part. But let's go ahead and run the simulation anyways and see what happens to our stress now that we have a finer mesh in that region. So go ahead and click submit. Okay, reviewing the results. Now let's look at our stress. So as we can see, our stress has increased. So we're now at about 5.9, and I believe before about 5.4. And the reason is because we create a finer mesh. So if we kept doing this and we kept increasing the number of elements in that region, we can also increase it going outward as well. We'll see that the stress increases, but it will eventually reach a constant value no matter how much more fine of a mesh you make, and that's how you know if your stress converges. So we'll go ahead and show you one more thing. I'm going to click seed edges, and we'll change the seeding on these edges here, and we'll now make it 20. Okay, leave the mesh in that region, and we'll change this one again as well. So as we can see, we're really fine mesh in that region. If we wanted to make this perfect, we'd have to increase the number of elements leaving that edge as well. Because right now we have a 20 by 4 section essentially, but that would also increase the number of elements in all the other sections as well. And you might run out of nodes for your submission, which is just a byproduct of using the student edition of Abacus. So we'll view our results. And we see, again, we've gone up a little bit more to 6.13. Okay, and that concludes this video lecture.